Okay, everyone, welcome back to my channel. Today I'm going to solve this recover binary search tree problem. So the problem description is as follows. You're given a root of a binary search tree where the values of exactly two nodes of the tree were swapped by mistake. Recover the tree without changing its structure. Okay. Okay, the example given is as follows. So here in this binary tree, the value should be 1, 2, and 3, right? But these two values, 1 and 3, were actually mistakenly swapped. And we want to find out this mistake here and actually recover it back to the correct positions. Okay. So it's a binary search tree, right? And that means that if we do an in-order traversal, then if all of the nodes are in the correct position, then we should get back a sorted array or sorted list. Okay, so let's think about an example here. So suppose I have an array 1, 2, 3, 4, and there was a mistake, and it was mistakenly turned into, for example, if we mistakenly swap 2 and 3, then it would become 1, 3, 2, and 4. So if we do an in order, or if we start from the smallest element all the way to visit the largest element, then we would find some abnormal pattern here. So if we start from this element and compare it with the adjacent element, 1 is less than 3, all good. But here we come across something interesting. So 3 is greater than or equal to 2, which is not in a ascending order, right? So here we could just find out that 3 and 2 should be swapped. But I think there is another case that is more general. So if we think about swapping two non-adjacent nodes, right? For example, 3, 2, 1, and 4. Okay. So basically 1 and 3 are swapped in this case. Okay. So right now, if we do an in-order traversal or visit the array from the smallest to the largest, the first two actually just don't really follow the pattern, right? Because 3 is bigger than 2, and the second pair is also not following the ascending order because 2 is greater than 1. Okay, so in this sense, in the first two abnormal pattern, okay, the left-hand side element is the one we should record, right? And the right-hand side element of the first pair we encountered could be another mistake, or could be in its original position. We don't know, so we keep visiting until we visit the second abnormal pair, which is 2 and 1, and then we know that the right-hand side element of the second pair, which is 1, is actually the abnormal one, or is the mistake one. Okay, so 3 and 2, the first pair that is abnormal, the left-hand side element should be the mistake, and the second pair, the right-hand side element should be the mistake. Okay, so we now find the pattern here. So 2 is just an intermediate element with nothing to do here, right? If we do another example, if we swap 1 and 4, then the case would become 4, 2, 3, and 1. So the first abnormal pair is going to be 4 and 2. And we know that the left-hand side part is actually the mistake one. Okay, we record it down. And we keep iterating. Okay, 2 and 3, all good. Okay, 3 and 1, abnormal pair because the previous element is bigger than the current element. Okay, so we know that in this case, the right-hand side of the first of the second pair is abnormal element. So in this case, we know that we should swap 4 and 1. Okay, in this case, we should swap which one? Which is 3 and 1, right? And of course, in this case, is just 2 adjacent element. We should swap 3 and 2. Okay, so that's some pattern we found. So I guess right now it should be clear that if we just do an in-order traversal and keep for any let me see. For any current element at visit, I compare it with the previous node I visited, okay, and see if it's an ascending order. If it's not, then basically I can record something down. Okay, so there will be 2 nodes that need to be swapped, so I'll keep track of them. Okay, non-pointers at the very beginning. Okay. And I should also keep the value of the previous node actually. So previous value is equal to, let's set it to be something like really small, right? Something like this. Okay. And I think we can do the order traversal now. Node, okay. Node is already none, okay. Then we don't actually need to do anything here, right? If it is not none, then firstly we visit the left hand side. Okay, the left child or the left subtree could be empty or could not be empty. Okay. So right now, and another thing, because this is in order traversal, then we should do the comparison here. Okay. Before visiting the right branch. Okay. So the next thing we can do is basically do the comparison. Okay. So remember the abnormal case, which is that the previous node has a value that is greater than or equal to the value of the current node. Okay. So in that sense, we need to decide whether it is the first occurrence or the second. Okay. So if it is the first occurrence, so first is still none, then basically we can assign first to be the let me see. Okay, I think I need to create a okay, I don't need to create a new node. Okay, I think I need to create a new node here to put the value inside the node rather than purely using a value, because the previous one should represent a node instead of just a scalar. Okay, so new should be tree node. Okay. So, okay. Previous node dot value. So here the first would be previous node. Okay. And if first is not none, then we assign the second one to be the current. Okay. Remember that this also includes the case where two adjacent values are swapped, because there is only one abnormal pair, and in the first appearance, both the previous node and the current node will be put into first and second accordingly. Okay. Okay, the next thing we need to do, so the previous node has finished its task, then we can just update its value right now. So remember, this is an in-order traversal. So we do all of the things here between visiting the left branch and visiting the right branch. Okay. So let's go to the node. Okay, so that's pretty much it. Return. Don't actually need anything in the return value. So in order traversal, So let's just call the in-order traversal, okay, on the root. And after that, we should expect the first and second to contain the mistakenly swapped nodes already. Okay, and then right now we just need to swap the values of the two. So we need a middle value, store the first one, okay, and okay, now we can, okay, now we can just put the value of the second node into the value into the first node, okay. Okay, and the last step we need to do is put the previously stored middle value back to the second node, okay. I think that's pretty much it. Yeah, so let's give it a submit test run, actually. Reference before assignment. Okay. It's not actually in the scope of this function, so do something here. I think it's the same thing with all of the other variables here. Okay. Let's make those variables to be class variables, actually. So that we can easily keep track of them inside the scope of the class. Okay. Is there anything I omit? Let me see. Okay, so previous node should always has a value that is smaller than the current node. If it's greater than this, then we then we need to check, right, which case it belongs to. Okay, let's check if this actually goes into the condition here. Self dot first, self dot second. Okay, let's just print it. Interesting. So first, let's see what the value actually is. Okay. In theory, we should see something. Okay, so it never goes into the, okay, it never goes into this if condition here. So let's add something. I haven't directly seen the error here. So let's just add some extra printing statement here. Okay, the assignment here is not successful. The assignment here. Okay. Oh, I see it. It's a very stupid error. Test case 2. Okay, it should be fine this time. Let's just move all the print here. Okay, great. Okay, although there was some stupid error, but luckily we've gone through it. Okay, that's great. And thanks for watching today's video, and looking forward to seeing you in the next videos. Have a good night.